At the center of an infant's daily life is a marvel of material science and high-speed mechanical engineering, designed to perform a deceptively difficult task. It must rapidly absorb large volumes of warm, biologically active liquid. Lock that liquid away so it cannot be squeezed back out under pressure, and maintain a soft, breathable, and perfectly dry surface against sensitive skin. To achieve this, a disposable diaper relies on a precisely orchestrated stack of highly specialized layers, each performing a distinct physical or chemical function, all assembled by continuous web manufacturing machines operating at speeds that defy human perception. Understanding how this object works requires looking closely at its anatomy, starting from the layer closest to the body and moving outward. The uppermost layer is known as the topsheet. Its primary job is to act as a one-way valve for liquid. It is made from a non-woven fabric, typically spun-bond polypropylene. In a non-woven fabric, plastic resins are melted and extruded into microscopic fibers that are laid down in a random web and thermally fused together, creating a material that feels like soft cloth, but is entirely synthetic. Polypropylene is naturally hydrophobic, meaning it repels water. If left untreated, liquid would simply bead up and roll off the top sheet, leading to immediate leaks. To solve this, manufacturers apply a precise coating of surfactants to the top sheet. Surfactants lower the surface tension of the liquid, allowing it to instantly pass through the microscopic spaces between the polypropylene fibers. However, because the plastic fibers themselves do not absorb any moisture, the top sheet remains completely dry to the touch once the liquid has passed through, protecting the skin from prolonged exposure to wetness. Immediately beneath the top sheet lies a critical component called the acquisition and distribution layer. When a sudden volume of liquid is introduced, the absorbent core underneath cannot soak it up instantly. Without a buffer, the liquid would flood the surface and leak out the sides. The acquisition layer acts as a temporary reservoir and a surge protector. It is typically a high-loft, non-woven material with an open, airy structure and large pore sizes. By utilizing the physics of capillary action, this layer rapidly pulls the liquid away from the top sheet and spreads it outward across a wide surface area. By dispersing the fluid longitudinally and laterally, the acquisition layer ensures that the underlying absorbent core receives the liquid at a manageable rate, preventing any single localized area from becoming overwhelmed. Beneath this distribution network lies the engine of the diaper, the absorbent core, which relies on a combination of mechanical wicking and advanced polymer chemistry to trap liquid permanently. The core is a highly engineered blend of cellulose fluff pulp and a remarkable chemical compound called superabsorbent polymer, or sodium polyacrylate. In its dry state, sodium polyacrylate looks like ordinary coarse white sand. At the molecular level, it consists of incredibly long polymer chains that are tightly coiled and bound together by chemical crosslinks. When liquid reaches the core, the cellulose fluff pulp, which is highly hydrophilic, wicks the moisture instantly, distributing it to the surrounding polymer granules. As water encounters the superabsorbent polymer, a powerful chemical process called osmosis is triggered. The concentration of sodium ions inside the polymer is significantly higher than in the surrounding liquid. To balance this concentration gradient, water molecules rush into the polymer network. As the water floods in, the tightly coiled polymer chains violently uncoil and expand, transforming the dry powder into a thick, rubbery gel. A single gram of this polymer can absorb and hold up to 300 times its own weight in pure water. More importantly, because the water molecules are physically bound within the expanded polymer network, the liquid cannot be squeezed back out, even when a baby sits or falls directly onto the saturated core. The ratio of fluff pulp to polymer is meticulously calibrated. If there is too much polymer and not enough fluff pulp, a phenomenon known as gel blocking occurs. The outermost granules of polymer would absorb liquid so quickly that they would swell into an impenetrable wall of gel, blocking the remaining liquid from reaching the dry polymer underneath. The cellulose fibers act as microscopic highways, keeping the polymer granules separated and ensuring that liquid bypasses the swollen outer layer to reach the dry material deep within the core. Wrapping this entire absorbent structure is the backsheet, the final line of defense. The backsheet must be entirely waterproof to protect clothing and bedding, yet it must also be breathable to allow heat and humidity to escape, preventing severe skin irritation. To achieve this seemingly contradictory set of properties, the backsheet is constructed from a microporous polyethylene film. During the manufacturing of this plastic film, microscopic particles of calcium carbonate, essentially crushed chalk, are compounded into the polyethylene resin. The plastic is extruded into a solid, waterproof sheet and then mechanically stretched. As the plastic stretches, it violently pulls away from the rigid calcium carbonate particles, tearing microscopic holes, or pores, around each particle. These pores are engineered to be less than 1 micron in diameter. The physics of surface tension dictates that liquid water molecules bind together in droplets that are far too large to squeeze through a 1-micron hole. However, individual molecules of water vapor and warm air are incredibly tiny and can easily pass through the microscopic labyrinth of pores. This allows the diaper to constantly vent humidity while remaining an absolute barrier to liquid. Along the edges of the diaper, running parallel to the legs, are the leg cuffs. These provide a dynamic mechanical seal against the body. Unlike the top sheet, the non-woven fabric used for the leg cuffs is treated to be highly hydrophobic, actively repelling liquid and forcing it back toward the absorbent core. The fabric is often a multi-layered structure called spunbond melt-blown spunbond. The inner melt-blown layer consists of exceptionally fine, densely packed microfibers that create a tortuous path for liquid, establishing a formidable waterproof barrier while remaining incredibly soft. Woven into these cuffs are stretched strands of spandex elastic, which gather the material to create a secure, flexible seal that moves with the body. Bringing these complex, distinct materials together into a unified product requires an assembly line of staggering scale and precision. Diaper manufacturing is a continuous web process. The machine is often over 50 meters long, pulling continuous ribbons of raw materials from massive spools, combining them, gluing them, cutting them, and packaging them at speeds reaching 1,000 diapers per minute. At these velocities, stopping the machine to change an empty roll of raw material is economically impossible. Instead, the machine utilizes automatic zero-speed splicers. When a massive roll of non-woven fabric or plastic film nears its end, the machine accumulates a buffer of the material in a towering structure of moving rollers called a dancer. While the machine feeds from this accumulated buffer, it holds the expiring tail of the old roll stationary and uses mechanical arms and heavy-duty double-sided tape to instantly splice it to the beginning of a fresh, full roll. A blade severs the remaining scrap, the dancer releases its tension, and the massive new roll spins up to operating speed, all without the main assembly line slowing down for a fraction of a second. Web tension control is paramount throughout the process. Every material, from the delicate tissue to the stretchy elastics, responds differently to being pulled. Load cells constantly measure the tension on each web, sending data to computerized drives that adjust the speeds of individual rollers by fractions of a percent to prevent the materials from wrinkling, snapping, or stretching out of shape. Ultrasonic sensors monitor the edges of the traveling webs, actively steering the rollers to keep the materials perfectly aligned as they speed through the machine. The physical heart of the manufacturing process is the core forming module, where the absorbent pad is built from scratch. Raw cellulose arrives at the factory in the form of massive, dense rolls that resemble thick cardboard. This high-density pulp sheet is fed continuously into a machine called a hammer mill. Inside the hammer mill, a heavy steel rotor studded with blades spins at over 3,000 revolutions per minute. As the dense pulp sheet is fed into the rotor, the blades brutally smash the material, breaking the mechanical bonds between the compressed wood fibers and shredding the sheet into a loose, airborne cloud of cellulose fluff. This fluff is immediately drawn by a massive industrial vacuum system into the forming chamber. Situated inside this chamber is a large, rapidly rotating forming drum. The outer surface of the drum is constructed of fine stainless steel wire mesh and features three-dimensional contoured pockets that are the exact shape of a diaper core. The vacuum pulls air fiercely through the mesh, drawing the airborne fluff fibers into the pockets. Simultaneously, sophisticated volumetric dosing feeders inject a precise stream of superabsorbent polymer powder into the tumbling cloud of fluff, intimately mixing the two materials before they hit the drum. The vacuum holds this loosely packed mixture of fluff and polymer tightly in the contoured pockets as the drum rotates. A rotating brush, known as the scarfing roll, aggressively sweeps over the surface of the drum, removing any excess material and ensuring the core has a perfectly flat top and a precise weight. As the drum reaches the bottom of its rotation, the vacuum inside that specific sector is momentarily shut off, allowing the newly molded, three-dimensional absorbent core to drop gently onto a moving conveyor belt, where it is immediately enveloped in a thin layer of tissue or non-woven core wrap to contain the loose polymer dust. At this stage, the core is highly aerated and far too thick. It passes through a series of heavy steel calender rolls that apply extreme hydraulic pressure, compressing the core to a fraction of its original thickness. This densification not only makes the final product thinner and more comfortable, but also decreases the distance between the microscopic cellulose fibers, significantly increasing the capillary action that gives the core its wicking power. As the continuous ribbon of compressed cores travels down the line, the other layers are introduced. The waterproof backsheet is unwound and fed beneath the cores, while the acquisition layer and the hydrophilic topsheet are fed over the top. Bonding these distinct layers together at high speed without compromising their flexibility or breathability requires highly specialized adhesive technology. Standard liquid glues would dry too slowly and make the diaper stiff. Instead, the machine uses hot melt adhesives. Solid blocks of thermoplastic adhesive are melted at over 150 degrees Celsius and pumped through heated hoses to application nozzles. These nozzles do not simply smear the glue onto the fabric. Instead, they use jets of heated compressed air to whip the microscopic streams of liquid adhesive into chaotic, swirling patterns, laying down a spider web-like matrix of glue. This fine web provides immense bonding strength while leaving the vast majority of the fabric surface open and breathable, ensuring the diaper remains soft and flexible. Applying the elastic strands for the leg cuffs involves a delicate balance of tension and adhesion. Continuous threads of spandex are aggressively stretched as they are pulled from their spools. Hot melt adhesive is applied directly to the stretched threads, which are then sandwiched between the layers of the hydrophobic cuff material. The adhesive must have exceptional creep resistance, meaning it must instantly lock the highly tensioned spandex into place and refuse to yield, even when the hot glue is still cooling. When the final diaper is cut and the tension is released, the spandex snaps back to its original length, gathering the fabric into the familiar ruffled leg cuffs. Applying the fastening tapes introduces a complex mechanical engineering challenge known as the cut and slip process. The fastening tapes are small, discrete pieces that must be attached to the continuous, fast-moving diaper web. The tape material is fed into the machine as a continuous ribbon at a relatively slow speed. It passes over a specialized vacuum anvil roll that is rotating at the much higher speed of the main assembly line. A rotary knife strikes the anvil, cleanly cutting a small segment of the tape. Because the anvil roll is heavily ported with internal vacuum lines, it instantly grips the small, freshly cut piece of tape. The vacuum secures the tape as it accelerates violently to match the surface speed of the main diaper web. The rotating anvil roll then stamps the fast-moving piece of tape precisely onto the passing diaper, where adhesive permanently bonds it in position. This high-speed mechanical ballet allows countless small, discrete components to be continuously applied with millimeter precision. With all the layers, elastics, and tapes fully assembled, the continuous web of material finally resembles a continuous chain of diapers. It passes through a massive rotary die cutter to establish its final shape. This unit consists of a hardened steel cylinder with razor-sharp cutting blades machined directly into its surface, rolling against a perfectly smooth, hardened steel anvil roll. The tolerances between the blades and the anvil are measured in microns. The blades crush through the layers of plastic and non-woven fabric, punching out the contoured leg holes. The scrap material from the leg holes, known as trim, is instantly sucked away by high-pressure vacuum tubes to be recycled or discarded. A final rotary knife performs the end cut, severing the continuous web into individual diapers. Instantly upon being separated, the diapers enter the folding section. High-speed mechanical plowboards catch the edges of the diapers, folding the side panels inward. Rotating tucking blades and vacuum belts fold the diaper in half longitudinally. The folded diapers are tightly stacked and pass through compression conveyors that squeeze the trapped air out of the thick materials. Heavy mechanical pushers ram the highly compressed stacks into polyethylene bags, which are instantly heat-sealed. Because the machine operates at velocities far exceeding the capacity of human vision, quality control is entirely automated. Throughout the entire length of the production line, a battery of high-speed industrial cameras and infrared sensors meticulously inspect every single product. Strobe lights freeze the motion of the web thousands of times per second, allowing the vision system computers to analyze the geometry of every diaper. The computers verify that the adhesive patterns are continuous, the core weight is perfect, the tapes are positioned with sub-millimeter accuracy, and no metal contaminants are present. If a camera detects a flaw, such as a skewed tape or a folded leg cuff, the system assigns a virtual tracking tag to that specific diaper. The machine tracks the defective product as it moves down the line at incredible speed. When that exact diaper reaches the end of the line, a precisely timed blast from a high-pressure air nozzle fires directly at it, blowing the defective diaper out of the product stream and down a rejection chute, guaranteeing that only flawless products reach the packaging equipment. The result of this immense industrial orchestration is a remarkably sophisticated piece of single-use engineering, manufactured by the millions with absolute consistency, relying on complex fluid dynamics, polymer chemistry, and high-speed mechanical automation to perform perfectly every time it is used.